Yes, hello everyone and welcome to the live. How are you people? So today we have finally reached to our lecture number 5 and yes we are uh, moving little with a slower pace, but I am trying to cover each and every topic without skipping any topics. That's why we have still not reached to the epoxide opening part. I will try to cover up the previous portion first because I don't want to skip anything. That's why. So this is our reaction mechanism series, which is going to be completely in English medium for those students who face Hindi as a barrier for understanding chemistry, and especially students from our South India who faces problem in Hindi. This is for you also. That because there were so many requests to start sessions or start batches in English. That's why we are trying and we are implementing this for you people. And of course, everyone can watch this. English is a very common language. So, what we have studied till now is we have covered the basic portions. We have seen how a substitution reaction works. We have seen two approaches: how a classical theory explains a thing, how your molecular orbital theory can explain a thing. We have covered these all things, and for now, today we will be starting with the mechanism portion. Good morning, Vishal. Good morning, Praful. Good morning, Shreya Das. Good morning, uh, Itaram. Good morning, Amrapali, Brajraj, Amit, Pragriti, Adi. आप सभी का स्वागत है and I welcome you all and good morning. Very good morning to everyone. So in today's lecture, we will starting with straightforward the mechanism portion. But before that, I want to give you a little recap what we have studied. In case few students who are watching this lecture for the first time, we have already covered 4 lectures, I think. No, this will be our 4th lecture. So please take care of this. Lecture number 1 was not conducted. So this is our lecture number 4, I think so. Okay. Now, today we are going to start with substitution reaction. The first mechanism that will be SN1 mechanism. If time permits, I will be covering the SN2 also. Let's see how it proceeds. But first of all, let's take a little recap what we have studied in this reaction mechanism topic. We have divided this topic into 3 fragments. One was substitution, one was elimination, and third was addition. Few more additional topics were added if you are preparing for NET and GATE. For example, Hammett equation, very important, and fragmentation reactions, very important. Again, looking CSIR NET and GATE exam. We have seen the solvent effect, how a solvent can affect the nucleophilicity. There are two types of solvents. One, we have a polar solvent and we have a polar protic solvent and a polar aprotic solvent. One of them increases the nucleophilicity, one of them decreases the nucleophilicity. Now we will also understand why in a SN1 reaction we particularly use polar protic solvent, why in SN2 reaction we use polar aprotic solvent. If we have understood these things, then from there will, when we will study these things into SN1 and SN2, these things are going to become very easy for us. Similarly, in polar protic solvent, I already told you the nucleophilicity decreases. In polar aprotic, it increases. Now we have seen certain things about living groups. What is which living group is an excellent living group? If it is eliminated and the anion is very much stabilized, then we say that yes, the living group tendency is very good. This was some order of living groups. There are certain living groups which we generally uses, and this should be the stability of the anion also, and same there will be, it will be its living group ability also. In yesterday's lecture, we were focusing on the MOT approach of a substitution reaction. It gives a completely new picture how a different theory, that is molecular orbital theory, can explain a substitution reaction. We learned that in order to have a good substitution, the gap between the HOMO of a nucleophile, which is generally a non-bonding orbital, and a LUMO of a substrate, which is generally a sigma star orbital, should be very less. If the gap is less, then the rate of nucleophilic substitution reaction is also very good. These all are the things which we have covered in the yesterday's lecture. Okay. I hope so. You enjoyed yesterday's lecture. You get to know a new approach. You get to see how these things work with the help of MOT. We have taken this example and explained why in the case of CF, the nucleophile is acting as a base, and why in the case of I, it is acting as a nucleophile. Then we have drawn the MOT diagram. This was the MOT diagram. We found the best nucleophile whose HOMO is higher in energy, and we found that the best substrate is that which has is LUMO, lowest in energy, so that the gap reduces and HOMO can, the lone pairs, or we can say the electrons in the HOMO can easily be donated into the LUMO of the substrate. These things what we have covered. I explained this contradiction, why this happened here, and an example proved this also. Uh, when I was doing a substitution reaction with PPS3, it took me 3 days to do so. But if I add a small amount of catalyst Ki, because of I minus being a good nucleophile, reaction was very fast. And when a substrate forms, this substrate falls into category of excellent substrate also, because its LUMO is very lower in energy, so PPS3 was able to attack very easily. So overall this reaction just finished into 3 seconds. So this was the role of catalyst into the reaction. Now for, I promised you to start the SN1 part in today's lecture, so here we are. First of all, we will cover with the SN1 reaction. I hope you are full pack ready, and you are making notes, you are preparing your notes, because these notes are going to help you for any exam. You are going to revise these notes after and after, again and again, so that it get memorized. You memorize each and everything of the notes part, and you need to practice a lot of question also. So talking about SN1 reaction, this is something which we are studying from, I think, class 12th. uh, we all know that SN1 reactions take place in 2 steps, but there are few small things which we generally miss or we don't take care of, that I will be focusing on, so that this SN1 reaction is completed. We can complete this into a holistic way. See, talking about SN1 reaction, we also say that this is called as unimolecular nucleophilic substitution reaction. Unimolecular nucleophilic substitution reaction. Why we call this as unimolecular? This we will be covering right now only. Unimolecular nucleophilic substitution reaction. We all know that this SN1 reaction takes place in 2 steps. So I will be taking a very general substrate. Let's suppose we have RCH2 and a X group. In the first step, first of all, the living group is eliminated from here. Let's suppose this X minus living group is eliminated, and what we draw is a carbocationic center. Let me take a more substituted center. Let's suppose we have 3 R groups here. Now, since the living group is eliminated, in the first step we have formed a species which is called as carbocation. Now, in the second step, what happens is, we have our carbocation, and on this carbocationic center a nucleophile attacks. Let's suppose I have chosen a nucleophile. This will attack on the carbocationic center and we will form our product. But in most of the cases when we deal with SN1 reaction, what is the actual picture? We see that instead of choosing a nucleophile in a SN1 reaction, in, I will say, 90% cases, we choose a solvent molecule. For example, let's suppose I have water as a solvent. Now this water molecule will attack at the carbocationic center and will form the product. It means instead of choosing a nucleophile separately, the solvent molecule which we have used in the SN1 reaction will act as a nucleophile. See, in previous lectures, I have thrown a concept of solvation in front of you. What does solvation means? When your solvent molecule approaches the cation or any anion and forms an ion dipole interaction, this was called as solvation. But when a water molecule or any solvent molecule attacks on the carbocationic center and one of the bond breaks, remember bond breaking is very important, then in such a situation this type of reaction is called as solvolysis. In solvolysis, The word lysis means breaking. That's why it is very important the bond should break in this step. Once the bond is breaked, we form a product which looks like this, R, R and we have an OH group. So this will be our final product, but this step is called solvolysis step. You must have observed in some previous year questions also, instead of asking tell me the rate of SN1 reaction, examiner asks you tell me the rate of solvolysis. It means he's trying to ask you the same rate as that of SN1 reaction, which depends upon the rate of formation of carbocation only. You always compare the rate stability of carbocation in order to tell the solvolysis. Why you do so? Because it is same as that of SN1 reaction. If instead of a nucleophile, which happens in the 90% of the case, if solvent molecules attacks on the carbocation, some sort of bond breaks, then this step is called as solvolysis. If I become specific, this step will be called as hydrolysis. If I have ammonia as a solvent, this will be called as aminolysis. Did you got the concept? So in the step 2, either first one will be going to take place or either second one is going to take place, but in 90% of the case this second condition where the solvent is acting as a nucleophile happens in the SN1 reaction. Now if I represent these two reactions on an energy profile diagram, what is an energy profile diagram, sir? Let's suppose I have an y-axis here and an x-axis here. On x-axis I am writing progress of reaction, or some books also use reaction coordinate. Both the things are same. What does this mean? Means how the reaction is proceeding in the above two steps. We are trying to represent these two steps on a graph. How the reaction is moving, we will try to represent this on the x-axis. And the y-axis is called to have a potential energy. It means if I move up, the energy of the molecules are going to increase, and if I move down, the energy of the molecule is going to decrease. Now how we can represent these two steps here? See, let's suppose we start with a reactant and its energy lies somewhere here. We have a reactant at this position. Whenever you proceed a reaction, you give certain amount of activation energy in order to reaction to happen. Let's suppose in this case, I am thus just creating a hypothetical situation. We start to heat the reaction. In lab also to do any organic reaction, either you provide a sunlight, either you provide heat in the form of you light up the burner and you heat the solution. So I am creating a hypothetical situation so that we can understood this. Let's suppose we have heated the substrate. It means its bond are going to vibrate and the bond are going to break and the energy of the molecule is going to increase. So the energy of the reactant goes on increasing and it reach a maximum value and suddenly the bond breaks. The form of reactant which is in highest in energy. The reactant which is in highest in energy is called as transition state, and this I called as transition state number 1. And how it is going to look like? You have a substrate here where this carbon and a living group bond is going to break. So these will be R group. Since this dash line is breaking, I will be writing a B here, and this is the way to represent a transition state. This is how your first transition state going to look. Once the bond has completely break, then you are somewhere here at the carbocationic center. This is what your first step is going to look like. Now for the second case, what is going to happen? Now the nucleophile is going to attack at the carbocationic center and the product is going to be formed. So let's suppose somewhere here we get our product. This is our product and this second state is called as transition state 2, and in this second step the bond is forming. So how it is going to look like? See, you will be having a carbocationic center where the nucleophile is going to be attached, and I write F because the bond is forming. Now if we compare these two steps. And if we see this energy gap between the transition state and the reactant, this is called as the activation energy. This is called as the minimum activation energy which we require in order to make this reaction happen. If we are not able to supply this activation energy, this reaction is not going to take place. Since highest amount of activation energy is required for the step number 1. So that's the reason step number 1 will be the slowest step. So we always write step number 1 as a slow step because the amount of activation energy required to make this reaction happen is highest for step number 1. And the reaction which is the slowest step, and we can say the step which is slowest among the reaction, is your rate determining step. So we very often write in a SN1 reaction that step number 1 is going to be our rate determining step. Now I have explained this also why our step 1 is here an rate determining step. Did you get the concept? How I plotted the reaction on the graph and how I called the step number 1 as a rate determining step? Do tell me in the comments. Good morning Sonam, good morning Ankita. So there are small few things which I have added in your knowledge for the SN1 reaction. You must be knowing before also what is an SN1 reaction, but small things like solvolysis, like this graph, which I must have added. Okay. Good morning, very good morning, Diksha. So this energy gap is very important to understand. This is called as activation energy gap, and this is the minimum energy which you will supply in order to make this SN1 reaction happen. Because the first step has the highest barrier, it will be the slowest step, and the slowest step is always your rate determining step. That's the reason I have written the first step as RDS step. If you have understood this, then we are going to move on the rate equation. We always write rate for that step which is slowest in the reaction, and here it is the step number 1. Step 1 says that in the rate equation you only have your substrate, so rate is going to be directly proportional to concentration of substrate only. When I remove the proportionality sign and we get a constant, so we can write as rate is equal to rate constant, and the reaction will be first order with respect to substrate. That's the reason SN1 reaction is also called as unimolecular reaction, because this is a first order reaction with respect to substrate. This is a first order reaction with respect to substrate. Did you get this? Solvolysis are also called as what's you have written? No NGP reaction. No. Why we will call solvolysis as NGP? Sanam. NGP means neighboring group participation. A group which is a part of the reactant will participate. Here solvent is not a part of the reactant. So why you think so ki we should call this as NGP reaction? How this thought originated in your mind? Hmm? Never. We cannot call solvolysis as an NGP reaction. कब हुआ ये NGP? When we will cover this NGP reaction, you will get that concept also. See, in an NGP reaction, generally the group which is present in the reactant molecule will eliminate the living group. That's why its name is neighboring group participation. Whenever you get the question to answer the rate of solvolysis, you just need to compare the order of, or you can just need to compare the stability of carbocations. Okay. We will do some questions also in order to clarify your doubts. So this is the basic portion which we study for an SN1 reaction. Don't uh, mess it up in your notes. Try to write it down separately because I have little less space, so I have congested this. So now what we are going to do is, now we will draw some conclusions on this what we have done right now, and we will write down few points which will make us understood this SN1 reaction more better. So the point number 1 says that there is no role of nucleophile. Why? What does this point number 1 means? Where the nucleophile is not playing an important role. See, if I talk about the rate equation of an SN1, we saw that it only depends upon the concentration of substrate, correct? The reaction is first order with respect to the concentration of substrate. Since your nucleophile is not present into the rate expression, if we increase or decrease the concentration of nucleophile, whether the rate of SN1 will be affected or not. There will be no effect on the rate since nucleophile is absent in the rate equation. That's why we have written that there is no role of nucleophile in a SN1 reaction. And that's the reason we generally use solvent molecule as a nucleophile, since nucleophile does not play any important role in deciding the rate of reaction. That's why in most of the cases, the solvent molecule will act as a nucleophile and it will perform the SN1 reaction. Try to link each and every point, then you will be able to get this SN1 reaction in a very holistic way. This rate expression does not contain any nucleophile, and generally our nucleophile is a solvent molecule only. So this was our point number 1, that there is no role of nucleophile. Should I move ahead? See, what's the next point, sir? The next point is very important. It is saying that rate of SN1 reaction. Examiner can ask you straightforward, tell me the rate of SN1 reaction, or he or she can ask you, tell me the rate of solvolysis. Because both the reactions are very much similar. If the solvent molecule attacks, we call that step as solvolysis. So its rate also depend upon the same on which the same factor which is deciding the rate of SN1. So what we say that rate of any SN1 reaction is directly proportional to stability of carbocation, stability of a carbocation, and one more factor which can decide is, which we generally miss, is rate of formation of carbocation. Rate of formation of carbocation. This factor also decides the rate, whereas first factor also decides the rate. This is a very important factor which we generally miss. CSIR NET has asked question on this. Recently, if we have given the UPSC Geoscientist prelims exam, that portion in that exam also the question was asked on this rate of formation of SN1. Sorry, rate of formation of carbocation. See, what we study generally is, we need to compare the stability of carbocation, but sometimes steric factors also play an important role. It means the carbocation which will be formed with the fastest rate will have the greater rate for an SN1 reaction. We will see few examples over this, then only the concept will be clear. So UPSC Geoscientist prelims exam, which happened recently on 18th of Feb, I think, they also asked the same it was not the same question, but it was the question based on this concept only. Okay. Now, You need to understand the stability of carbocation and you need to understand the rate of formation of carbocation. I will take an example. Let's suppose I have few groups here, oxygen, carbocation at this center, oxygen and a carbocation at this center. We have a nitrogen center. For this situation, I have drawn the carbocations and then I am asking you, let's suppose I have these four substrates. I told you this goes via K1 rate, this goes via K2 rate, this goes via K3 and this goes via K4. Can you tell me what will be the order for SN1 reaction or what will be the order for solvolysis? K1, K2, K3, K4. You have four substrates. सर CG सेट सिलेबस भी कवर कीजिएगा AKG motivation TV. Of course, we will cover that. See, if you are studying organic chemistry, what I am teaching here, it will cover holistically each and every syllabus. Main target is our CSIR net, and but the CSIR net syllabus is so vast that any other exams come under this only. Just you need to practice questions, okay? This is a very simple question which is on the basis of stability of carbocation. Here steric hindrance does not play any important role. You just need to arrange each and every carbocation on the basis of their stability. 4312, 3142, 2431. Why so much of different answers? Let's see. See, if I look at this oxygen, this is applying plus M effect. If I look at this carbocation, this is not getting any sort of plus M for the oxygen because at this center, the hybridization sp3, there is no sort of resonance possible. If I look at this nitrogen, yes, this is also getting plus M effect. If I look at this oxygen, this is also getting a plus M effect. It means it was clear cut that K2 is going to be with a minimum rate of SN1 or solvolysis. Now, oxygen is also applying plus M, nitrogen is also applying plus M. The plus M donating tendency will be higher for nitrogen center because its electronegativity is less. So of course K3 is going to be have the highest rate and then comes your oxygen one. In oxygen we have K1 and K4. Since this oxygen has a lone pair which is involved into cross conjugation, it means it has to do the resonance that way also and this way also. So of course the extent of donation will be little less as compared to your K1 case. So the overall order should be K3, K1 and K4 and then K2. So this should be your correct answer. K3, K1, K4 and K2. Did you get the concept? Sir, more inversion, less retention. Why sir? 4312. I have not taught anything about retention and inversion. Let me come there also. I will explain you why in SN1 reaction we see a little bit more of inversion and little bit less of retention. I will be covering that point, Amit. Just wait uh, and wait patiently. That will be also coming up. Okay. Now let me ask a question on this one. This second factor one. Let's suppose you have two type of groups. Uh, you have a phenyl ring, you have an oxygen, and to this oxygen we have attached, let's suppose one this group, and to the second we have attached, I don't remember the exact question but I am trying to form a question based on which has been asked in your exams. Let's suppose I have these two substrates. I say that this goes via K1 rate and this goes via K2 rate. You need to tell me which will have the higher rate of SN1 or you can say which will have the higher rate of solvolysis. Can you explain? Either K1 will be have the higher rate or either K2 will be having the higher rate. Now you need to understand where the carbocation stability is going to work and where the steric factors are going to work. If the carbocation stability will be working, you will go via this factor, carbocation stability. And if steric hindrance is the factor which will decide, then of course you will decide on the basis of a rate of formation of carbocation. Which carbocation is forming with the fastest rate? In that way you will be able to decide what's going to be the rate order. See, K2 higher, K2 higher. This is the mistake which you make here. See, we have two kind of substrates. One, this center is also sp3 hybridized, this center is also sp3 hybridized. Here the scenario is we have three CH3 groups attached to the sp3 center, but in the first scenario we have three tertiary butyl groups attached to the sp3 center. You can imagine the amount of hindrance it is facing at this center. So many bulky groups at a single sp3 center. It means there is so much of steric hindrance that now the hindrance will be the deciding factor. This group will be eliminated with a very fast rate. It means here the carbocation are going to be formed. Since yes, you are correct, the carbocatanic center formed in first situation will not have any alpha hydrogen, but in the second case it will have I say 9 alpha hydrogen. But the deciding factor is steric hindrance. What we see is whenever the substitution reaction take place, in the first step this carbocation is formed. If I say this first step goes by a very fast rate, and this time the deciding factor is the steric hindrance. That is what I am trying to convey here. Because of the hindrance, this group is going to leave with a very fast rate, and once the carbocation is formed, the hindrance is going to be relaxed. The stability of carbocation comes when both the carbocation has been formed, but the steric hindrance factor will be acting before the carbocation has been formed. Once you have formed the carbocation, then you can compare the stability, and then you can tell which will be formed by a faster rate and which will be formed by the slower rate. But steric factor is working before the carbocations has been formed. It is deciding which is going to form first and which is going to form last. So because of hindrance, the rate in the case of K1 will be faster as compared to K2. Did you get this or not? This type of questions are asked in CSIR NET exam, and yes, this time UPSC Geoscientist Prelim also asks the same concept. Did you get the concept? Is it digestible for you? This is not what you study in class 12th and your graduation. You need to upgrade your level. You need to upgrade for your SN1 knowledge also. It is not going to be same always. Yes, you are going to give CSIR NET exam, which is one of the most highest level exam in your subject. Of course, this type of concepts will be asked there. Yes, here the steric factors will be the first priority factors. Got this? When I will be taking a practice session of questions only, I will discuss all the previous year questions which has been asked on such type of in such type of exams like CSIR NET, UPSC, Geoscientist, or any GATE exam or any assistant professor exam. In that practice session, which will be the next week from Wednesday, Thursday, and Saturday, I think. In that, I will be covering these type of questions only. For now, I am focusing on the concepts so that you can prepare your notes well and you can revise them well. Okay. सर अगर स्टेबल कार्बोकेटाइन K1 is more stable bond angle 120 डिग्री. You are trying to explain the carbocation stability on the basis of bond angle. See, the deciding factor which will be, no, it will be the steric factors, but before the carbocation has been formed, it is working in the reactants only. So you can compare from that way also. If you feel comfortable in this way, you can compare this way also, no problem. Okay, that is why what I am trying to explain you, Sanam. The carbocation has been formed uh, when after the steric factors. The steric factors are deciding which carbocation will be formed with a faster rate. Okay. This same question has been asked in your CSIR NET exam also, if I am correct. I do not remember the exact question, but the concept was like this only. Should I move ahead? Is this digestible to you? First, you need to apply the steric factors, and then if it is not that dominant, then you will go with the carbocation stability. Let's move ahead. The point number, we have covered 2 points. No, there was no role of solvent in deciding the rate. When we see the solvolysis or the SN1 rate, there are two factors which are working. The third is the product formed is racemic mixture. We often say that whenever a SN1 reaction proceeds, we form a product which is racemic mixture. Let me explain how this works. Let's suppose we have a substrate here. We have let's suppose a X group here. We have a hydrogen group here. We have chosen X, no, we need to change this group. Let's suppose we have a CS3 here, and at this center we have any R group here, or let's say, let us take real examples. We have a deuterium here. Now what, but we need to have some stable carbocations, no. Let's suppose we have a phenyl group here. Once this X group is eliminated, what we form is a carbocation. And of course, once a carbocation is formed, this center is sp2 hybridized. We have a pH center, a vacant p orbital. Now the nucleophile, which is very often the solvent molecule only, so I will be using a simple water molecule. It can attack in this lobe also, it can attack in this lobe also. So we can form two products, and the two products will be looking like, let's suppose we have a OH at this center, then again we will be having a CS3 here, hydrogen here, and a pH here. If I form a product from this side, we will be having a carbon and a OH here, again above the plane CS3, below the plane hydrogen, and a phenyl here. Now what we see this, one of the product is our inversion product, and one of the product is our retention product. It has the same configuration as that of the starting material, so it will be called as a retention product. And if it has a different configuration than the starting material, it will be called as the inversion product. Because there is 50% chance to attack at this center, there is 50% chance to attack at this center. Now let's suppose in a reaction medium you have equal amount of R and S configuration molecules. If you have equal amount of R and S molecule, of course the final solution is going to be a racemic mixture. And racemic mixtures, remember, every time they are optically inactive because they do not rotate the plane polarized light. But this situation which we have written here is a hypothetical situation. It is an ideal situation. This does not happen every time in a SN1 reaction. Someone has pointed it out, sir, why inversion products are more? It means, who was that? Amit was trying to say that. Let me see the comments. Who was trying to point this out? Amit was trying to point why the inversion products are more. So see, this situation which I have created here is a very hypothetical and ideal situation where 50% inversion products are forming and 50% retention products are forming. But the reality is little bit different. So first of all, copy this, then I will moving on the reality portion. Sir, आप looking like KL Rahul. अच्छा जी. अरे अरे, विलन अमरीश यादव कंट्रोल जी. What happened? Good morning, Rahul. Sorry, Rahul, not Rani. Good morning, Rani. Should I move ahead? This what we have find is an ideal situation where 50% inversion and 50% retention products are being formed. Have you copied this and understood this? Okay, let's move. See, the reality is whenever I look at an SN1 reaction, this mechanism is of course an SN1 mechanism. We find that the retention products are 47%. Very good. But the inversion products are 53%. It is not an ideal situation where we have 50% of retention product and we have 50% of inversion product. So what's the reason behind this? Why this happens? This can also be explained very easily. Let's suppose we have this situation here. What happens when the when the leaving group is eliminated from this center? We can form two type of carbocations. One which you are looking here, this one, and the second which you are looking here. See, what's the difference between both of them? The first one is saying that an ion pair is formed. The front side of the carbonium ion is blocked. What happens when your leaving group is eliminated? This leaving group charge, that is minus, and the carbocation positive, are interacted with each other. It means they are in some sort of interaction with each other. The leaving group has not been eliminated completely. So at this center, they are saying that some sort of ion pairs exist between the carbocation and the X minus. And because of this ion pair, the possibility of attack from this side is little bit blocked because of the ion pair. So the nucleophile is not able to approach from this side. That's why the inversion products are generally little bit higher in proportion as compared to the retention product. Did you get the concept why inversion was 53% and why retention was 47%? Yes, do tell me in the comments. Did you get this or not? So here the nucleophile has to attack from the back side only because the front side has been blocked by this ion pair formation. And of course, if the ion has been eliminated and it has been surrounded by the solvent molecule and it is far away from your carbocation, then no ion pair is formed, a free ions are formed. So both the faces of the carbocations are now free. Nucleophile attacks from both the side, from front also, from back also, and you form a racemic mixture. But since inversion products are formed in little higher amount, that's why your final solution will also be little bit optically active also. Yes, Camp Pacific, I understand this thing. अगर मैं अपनी लैंग्वेज में होता तो it would be a really एक अलग ही बात होती, पर we have planned this lecture series on English, so I am trying to speak and I am trying to explain all the concept in English only. Okay. See, दीक्षा एक बार फिर से समझाता हूँ ना, थोड़ा सा हिंदी में समझा देता हूँ, फिर आई विल कमिंग बैक टू द इंग्लिश. देखो हो क्या रहा है ना यार, जैसे ही लिविंग ग्रुप बाहर निकलता है, लिविंग ग्रुप निकला, लेकिन लिविंग ग्रुप पूरी तरीके से छोड़ के नहीं जा पाता, और जो कार्बोकटायन है और जो अनायन है ये एक दूसरे से इंटरेक्ट रह जाते हैं. जैसे तुमने आयंस नहीं देखे हैं, सोडियम पॉजिटिव X माइनस, अरे जैसे आयनिक कंपाउंड्स होते हैं वैसे ही ये एक दूसरे से इंटैक्ट रह जाते हैं. तो यार वो जो आपका उस साइड का लोब है ना पी ऑर्बिटल का, वो ब्लॉक्ड हो गया है। न्यूक्लियोफाइल उधर से आ नहीं पा रहा है, उधर से आएगा नहीं तो फिर इसी साइड से अटैक होगा और ये इन्वर्जन का ही प्रोडक्ट देगा। तो ऐसी सिचुएशन के अंदर इन्वर्जन के परसेंटेज तो बढ़ने तय हैं, इसीलिए ये बढ़ गया है। समझ में आया दीक्षा? गॉट दिस कॉन्सेप्ट और नॉट? So this is the actual scenario for any SN1 reaction. Do copy it fast and we will be moving ahead. There are few points we need to discuss, few more points for the SN1 reaction. Done? The second question, ionic bond is more stronger. Stronger, why is? Sir, you know chemistry concepts not will be easily clear, always forgetting. Sir, you know chemistry concepts not will be easily clear. Means I think you are trying to ask Ankita ki you forget the concepts very fast. So you need to revise your notes on a repeated mode. Okay. See, the next point is we generally prefer polar protic solvents in a SN1 reaction. Remember this point, this is very important one. We always prefer polar protic solvent in a SN1 reaction. Why polar protic solvent, sir? What's its role here? Since we form a carbocation, in a SN1 reaction, these polar molecules, they come and they form an ion dipole interaction. We can say that they are doing ion dipole interaction, which is stabilizing our carbocation, and also this is trying to prevent the formation of ion pairs which we have just looked in the previous point. If this type of solvation phenomenon is going to take place, then in such a scenario the ion pairs will not be formed because this X minus will also be busy in doing solvation and it will not come to the carbocationic center to form the ion pair. Understood? That's why we use polar protic solvent, so that the carbocation is also stabilized and the leaving group which is eliminated into the step number 1 is also stabilized and it do not interfere with our carbocationic center. Okay, that's why we prefer polar protic solvent. Now, this phenomenon which you are looking here is called as solvation, but we all know that yes, after some time one of the water molecule will attack at the carbocationic center and the step from solvation will be converted to solvolysis and the products are going to be formed. Did you get the concept why we use polar protic solvents in the case of SN1 reaction? Because stable cation and anion stable reaction proceed forward. Yes, very good. सर, आपको आलोक सर जानते हैं? किसकी बात कर रहे हैं आप अमित जी? सवाल पूछ रहे हैं आप या सवाल बता रहे हैं आप? इज दिस क्लियर? आगे बढ़े। Okay, let's move to the next point, effect of leaving group. This is also very important. If Since in the first step the leaving group is eliminated and you form a carbocation, that's why we can say that yes, the leaving group ability will also decide the rate of SN1 reaction. Sometimes questions are asked on this concept also. Rate of leaving group ability is also directly proportional to SN1 reaction. Why? If your leaving group is eliminated with a very fast rate, the factor can be steric hindrance also, then also the rate of SN1 reaction will be very fast. Okay, if the leaving group ability is fast, then the rate of SN1 will be also fast. Okay. So these were the few points which we have studied about an SN1 reaction. These conclusions help us to do the questions which are asked in our exam. If examiner is, if let's suppose CSIR net asks a question from this portion, of course it will be a little bit standard question. Like we have just seen that it was asking on the basis of steric hindrance, which we are not familiar. So you need to practice such questions, previous year questions which have been asked into the exam, so that we are comfortable with this type of questions also. Okay. आलोक सिंह HOD है मेरे कॉलेज में. Okay. It's good to know, Amit. So the next thing which we'll be covering is next point, SN1 reaction forms a rearranged product. See, whenever we form a reaction, we form a product via SN1 path, we always form carbocations. So it is very necessary to rearrange the carbocation and then form the product. So always remember, the rearranged product for an SN1 reaction is the major product. So this point also becomes important. Yes, we always form a rearranged product for an SN1 reaction, since carbocations is formed and of course they are going to undergo rearrangement. Whether ring expansion will take place, then they will undergo ring expansion. Whether any group shifting will take place, so the groups will be shift, and always the rearranged product will be the major product. Once we have covered these few points and once we cover the SN2 reaction also, then we will study this SN1 and SN2 with together by comparing both of them, and we will try to practice questions also, so that we can get this topic in a very holistic way. Okay. Next, what we need to cover is SN2 reaction, but this we will be starting in the next lecture. For now, your SN1 basic concept has been cleared. The question part is remaining, which we will see into the upcoming sessions. I hope you understood the total concept of SN1. You get to know few new things about SN1. For example, like why the inversion product is little bit more, how steric hindrance can also decide the rate factors, these small things. For now, let us keep it this much only. We will continue the class tomorrow onwards. From, of course, the timings will be same, that is 9 a.m. We will meet again at sharp 9 a.m. and I will be starting with SN2 portion, and I hope we will cover that and we will practice some questions also. Thank you so much everyone. Take care. Bye bye and happy learning. Let's meet tomorrow again at 9 a.m. Don't forget the timings. Most of you join after 9:30 or 9:20. I request you to join sharp at 9 a.m. Okay. Thank you so much.